Good morning, everybody. Good morning. Or good afternoon or evening, wherever you are. Oh, it's 4 a.m. for someone. Oh my gosh. Thank you for joining us this morning. Thank you for joining us. Today, we're very excited to have with us Miss Lainey Antoniado, who will be sharing with us about experiments on the ISS. So this topic is especially relevant for any of you who are taking part in the starter category, where we have challenged you to design an experiment for the ISS that studies space weather. So I would encourage all of you to ask all your questions. Do use the Q&A box as usual, because it's easier for us to track the questions there, and we won't lose anyone's questions in the chat box. But yeah, we'll be sharing a little bit. Hopefully you will get an idea of what are the kind of experiments that you are allowed to do on the ISS. As you know, the ISS is a very highly restrictive environment, and there are certain conditions that you need to meet if you want to send an experiment up there. And hopefully it will also give you some ideas about the kind of experiments that you can do. So we're trying to encourage everyone to think a little bit out of the box. Chat is a lot quieter than usual, yes. We have a slightly smaller group today because this is a bit more geared towards just the starter category. And it's also Saturday, and I expect a lot of people maybe on a Saturday have some difficulties waking up. But yes, but don't worry, as usual, we will record the webinar and it will be sent to everyone who registered for it. So there's no worries about that. But yeah, I will hand it over to Lainey now to give her sharing and presentation.
Hello, everyone. I don't know if you can hear me.
We can hear you just fine.
Let's share my presentation. First of all, hello, everyone. Good morning, good afternoon, depending upon where you are in the world. Thank you, first of all, to the Singapore Space and Technology Ltd for having me today and for giving me the opportunity to connect with you. And I really believe that all of you in both the categories of the Space Challenge, you're one of the greatest minds in space exploration, and we're very excited to hear your solutions and hear your concepts. So today, we will have a small presentation upon the experiments on the ISS. As you will realize, the range of topics and the depth of expertise needed to understand the specifics of all the different experiments and the domains are very wide. So I will try to contribute to more specifically to the experiments that I have an educational background on, which is mostly on biomedical and life sciences, as well as on artificial intelligence research. But we will have also an overview of some of the key experiments of the ISS for the past 20 years that has been ongoing. And at the end, I will also touch upon some experiments for the ISS that I have worked or contributed on for NASA and for ESA, and hopefully I can learn from you as well and learn from your experiences through this interactive session. So as Jillian said, you can also type your questions, and I will also monitor the chat myself as we go along. So let's start by thinking through about the International Space Station. So I'm sure some of you have a better understanding of how it works and some of you less, but we will try to move on together and discuss a few facts and figures about it. So the International Space Station is an unprecedented human achievement, from conception to construction to operation and to long-term utilization of the frontier of space. As you can see in the slide, it has been ongoing since November 2000. It's on orbit, and it has it's monitoring more than 350,000 sensors, ensuring station and crew health and safety. 6 spaceships can be connected to the space station at once, so different countries can have different types of mission concurrently. The ISS orbits around Earth at about 250 miles up in space, more than 70,000 miles in orbit, and it has 16 orbits a day. So it is a multifactorial lab. And the analog with the iceberg that you see on the right hand of the slide, I think it's depicting the different challenges that we face as scientists when we are designing an experiment to go to the ISS. The journey from fundamental research or technology development to full commercialization can be very long. So in fact, it can take many decades to go from initial conception or discovery to a useful product or application of knowledge. So in many ways, it can be instructive to think of this in terms of this iceberg. Innovative scientific research and technological development can be thought as a source of possibilities and potential uses. From this base of new knowledge and capabilities emerges a very finite, very small element, which is promising, and it can push the boundaries of science. So before we think of the ISS and the different types of research that we can perform, let's have a little bit of an afterthought on the benefits that it can bring to society and to humanity. Almost as soon as the International Space Station was habitable, researchers began using it to study the impact of microgravity, of radiation, of many different disciplines and different space effects that are impacting our daily lives and perhaps may impact future colonies in space in different ways. So this unique scientific platform continues to enable researchers from all over the world to put their talents to work on innovative experiments that could be done, that could not be done in any other lab that is terrestrial. So in the areas of human health, telemedicine, education, and observations of Earth from space, there are already demonstrated benefits to human life. Here you can see some key breakthroughs. I would say that the benefits outlined in this slide serve as examples of the potential to create groundbreaking scientific discoveries. I will highlight from these advancements robotic surgery, which has been advanced like no other because of space, drug discovery and preclinical work, especially with a focus on muscle and bone loss, as well as different types of experiments that the Gene Lab at NASA is providing. And also, of course, remote sensing and telecommunications. This is something that we can see in everyday life. So here you can see an overview of what we call the map of science. So the science conducted on the space station has had impact on the 12 out of the 13 primary disciplines that comprise the basic map of all sciences. So the underlying base map is the widely used disciplinary classification system, and it's a layout algorithm known as the University of California, San Diego. And this is the map of science, UCSD. And each colorful circle that you can see is depicting, it represents a unique subdiscipline and is sized by how many scientific articles or publications are presented within that subdiscipline. So as you can all appreciate from this map, the ISS has been instrumental in advancing scientific knowledge across all disciplines. So this is just to verify the importance of investing to the ISS to have a return of this investment in different types of breakthrough knowledge. So I will start with a topic that is close to home. It's around cellular biology research and what can we do in this discipline through the ISS. So the definition of cellular biology used for the ISS research guide includes cell culture, tissue culture, and related microbial single-cell organism experiments. So in the last 4 billion years, life has evolved and adapted in response to many physical, environmental changes on Earth. However, one key feature, the presence of gravity, and at its acceleration rate of 9.8 meters per square second, this has not changed. Thus, microgravity on the ISS, that is due to the platform's continuous free fall around Earth, offers a very unique opportunity for novel discoveries of cellular and tissue adaptation. So in this slide, you can see, first of all, on the left side, the different platforms where cellular biology research can be conducted on board the ISS. Most of them are within the Columbus module. And you can see on the very left, the Advanced Biological Research System, which is a key single locker system providing 2 growth chambers. Its growth chamber is a closed system capable of independently controlling temperature, illumination, atmospheric composition. This can grow different types of organisms, including microorganisms, including plants, and also small arthropods. And as you are seeing these different platforms, I'm sure some of you might be thinking that this is not directly relevant today now to space weather, but I want you to start thinking of the technical parameters that these little boxes and bioreactors are offering in different disciplines, because this is maybe something that you can translate into your own experiment. So have an open mind and think through the different technical parameters, and as we go along, you might have a new insight about your own research and your own proposal. So the second one is, as you see, the bioculture system. This is very different from those of you, I assume some of you might be biomedical engineers here in this group. So it's very different from the bioculture systems that we have in research and university labs. The primary component, as you can see, is a hollow fiber bioreactor that is designed to deliver nutrients and remove waste by multiple tightly packed perfusion fibers. This is particularly suited for microgravity cell culture, where nutrients transfer is limited to diffusion. Examples of many different experiments that have flown on this include myoblast, osteoblast, fibroblast, endothelial cells, stem cells, muscle cells, and bone cells. Also experiments that I have worked on, as you can see on the right side, this is some pictures of an experiment that I was working on at NASA Ames. This is on the impact of radiation on the central nervous system. The experiment was done primarily on in vivo on animals, but also in vitro on different types of stem cells. And as you can see also, it is very difficult to miniaturize the bioreactors and translate a concept that is done in many different modalities in a proper lab in 2 or 3 different rooms, and then conducted into one small bioreactor. And then the third one, among the very many different modalities that we have on board the ISS for cellular biology, is the biotechnology specimen temperature controller. I think this has enabled a lot of different experiments to be conducted. It's a static tissue culture incubator. It is designed to allow multiple short-term experiments to be controlled simultaneously. This is why you can have many different controls in the different cell bags. So, as you can see, these discoveries can have applications. We can conduct experiments in biomedical research, in tissue engineering, in host toxin interactions, in host pathogen interactions, in vaccine development, which is very urgent nowadays, in drug sensitivity assays, and also drug discovery. So I made this slide because I wanted to touch upon a little bit on how sending an actual experiment to the ISS is quite different from what we used to do in the university settings. So here is a little bit of a roadmap where you can see from the point that of inception, of the point that where you have an idea and you're designing an experiment, you have to start by thinking the very basics. And as I said, you have to start thinking the technological parameters. How can you accommodate your experiments on the ISS, given that the ISS has very particular and specialized capabilities? You have to start thinking about the electrical power that your experiment might need, the thermal control that you might need, the data that you might need to exchange with the different computer settings that we have on the ISS. If you have a biological experiment, of course, the gaseous interchanges are very important. So you have to set these parameters first when you're designing the experiment to see if it's actually feasible to conduct it on the ISS. Then, so many different university labs and companies as well are sending proposals to ESA and NASA. And when a proposal is accepted as a space flight candidate, after undergoing scientific and also technical review, a flight experiment team is formed. So the development cycle is initiated, and then there are different phases, as you can see. There is the PI, the principal investigator, that will be supported by an assigned project scientist from ESA and NASA, who functions as the advocate and liaison for the PI and assists with the experiment development phase. And this is key for you to understand that you might be working, for example, for a scientific experiment at NASA or ESA, but you might not, and you might be developing, for example, the ground controls or the space controls for this experiment and doing hands-on clinical or scientific research. But you may not, for example, have the traditional path of work that you would do in the academia. For example, you may not be able to publish these results, and you might not be able to create publications, or because because some of the data might be classified, or because some of the data might be controlled by a patent or intellectual property. So following this, we have, the developmental phase of the experiment. You have, to define the scientific and operational requirements. This is done in conjunction with the scientists that you're paired with at NASA or ESA. You have to set the research objectives that are maintained during design, development, and flight. And this is key because you have to think of how, for example, if you have cells, or if you have, for example, a living organism or even an animal, you have to think how can, at all phases, even, for example, during launch and during harsh environments in space and during liftoff, how can your cells still survive these extra Gs that they will entail? So it is more complicated than any other university or institute experiment that you might have already completed. Then we have the implementation team role and the responsibilities. So the spaceflight implementation team is led by NASA or ESA or any other space agency that is conducting experiments in the ISS. And they provide a payload or a project manager. So the team works together to manage and implement the phases of the experiment on the development cycle. And then the project scientists from the space agency will work directly with the PI throughout this whole process. Then we have another phase, which is the definition, documentation, and testing of a spaceflight experiment. So while I was working at the European Space Agency in the astronaut training facility, a lot of the people, we were doing this type of work. We're testing the spaceflight experiments to make sure that in the replicas of the ISS that we have in Europe, it is in Germany, and in the US, it is in Texas, that these experiments can actually be performed with the bioreactors and inside the modules that they are destined to be performed in space. So this work is quite complicated, and of course a lot of red flags arise around this phase, where we realize that there are more restrictions or some gaps in the development and the strategic design of the experiment. So to complete a successful experiment in microgravity, you have to have a detailed analysis and definition of the proposed experiment, and all requirements of the execution of the experiment must be identified and described as a feasibility analysis. So then we have the development of the requirements, as I said. Following, we have the science ground testing. This is a very serious project because the project scientist and the flight experiment team will support the PI in defining the types of testing that will be required before flight in order to mitigate risks and increase the chance of a successful experiment. So we're trying to test it and have some dummy runs to make sure that when it's actually truly deployed in space, it will actually truly work. So this test would include such things as validation of new hardware, for example, and practice runs to optimize and streamline in-orbit operation. And the test results define and refine further the requirements, the procedures, and the hardware setting and configurations. As you probably have guessed, there is a lot of further documentation that is produced for its experiment. Literally, it's around 1,000 different pages of instructions for every scientific experiment that you see conducted in the ISS, from the simplest one to the most complicated ones. So then we have the ground controls. This is a very basic and very important stage at the experimental design. Proper ground control experiments are very essential for successful scientific sound spaceflight experiments, so that we can compare the different results, and also that the results are publishable. And as I said, they're not always publishable in the public domain, in the high impact factor journals that we know, but they might be publishable internally in what we call the technical memo, the ESA technical memo and the NASA technical memo. So this is the reason why a lot of scientists that are working for NASA and ESA, they may not appear to have a lot of publications in the public domain, but they are writing technical memos internally for NASA and ESA. So if appropriate, ground controls are defined, they can be performed on any time, and they are also taking into account provisions for other parameters, environmental parameters, for example, temperature, and other parameters that simulate actual flight conditions. And then we have another phase, which is the hardware biocompatibility tests. These are also very important. This testing is warranted in some cases to ensure that biosamples and other organisms or even animals do not encounter unexpected difficulties while housed in a payload system hardware under the prescribed experimental conditions. These, of course, are audited by ethical committees as well, right? So it is done by different committees that are checking whether they are abiding by the ethical standards in bioscience research. And then we have the project integrated test, where the different hardware operations and procedures on the ground may be warranted. The appropriate testing will be identified by the experiment team. Usually it's by the space agency, and then it's announced to the PI. And finally, we have an approval, and then you can actually launch the experiment to the ISS. So I think this will give you a little bit an overview of what it means to actually conceptualize an idea and make it happen and send it to space to be conducted in the ISS. So moving on, I would like to switch gears a little bit. And now, having in mind all these technical requirements that, as I said, they translate to all the fields of science. Let's think about the issues and the topics that are investigated on the space environmental effects. As you can see, there are two different pictures here that are depicting severe degradation of the different materials that are layering outside of the module of the ISS. And also the right one says large radiation-induced cracks in the outer layer of the insulation. This is because the space environmental threats to spacecraft components, they vary greatly depending upon the component of the materials, the thickness of the materials, and also the stress levels that they have to endure. So we also have to consider in this type of experiments the mission duration and the specific mission environment, including orbital parameters for the mission, the solar cycle and the solar events that you have in the previous sessions. I assume that you have a lot of discussion about what sort of solar events may impact different instruments in space. Also, the angle of the spacecraft and how it faces the sun is important, and the orientation of the different surfaces of the spacecraft with respect to the spacecraft velocity vector in LEO. So, as you can understand, there are many different aspects that you can study, ultraviolet, for example, radiation or ionizing radiation. The three main sources of charged particle radiation naturally occurring in space are galactic cosmic rays, solar proton events, and the trapped radiation belts. I'm sure some of you are experts of this, so you probably know more than me even. So for most materials on the ISS, the effects of ultraviolet radiation can overshadow any effects by particulate radiation. So depending on the polymer, particulate radiation can result in cross-linking or chain scission, similar to damage by ultraviolet. And it can result in polymer, for example, embrittlement. This has been showcased over the 20 years that the ISS is operating greatly. And another great effect is seen as well in avionics and different airplanes where, we can see single event upsets. We can see errors and latch-ups. And so this is a very important domain. Also, another domain where you can study, for example, different biomaterials and how they affect on different types of phenomena, for example, plasma. Similar high energy particular radiation is space plasma. So the plasma environment around the ISS is composed of approximately equal amounts of positively charged oxygen ions and free electrons varying with solar activity and altitude. Because of the differences in spacecraft velocities, because of the differences also in ion thermal energy and electron thermal energy, electrons can impact any spacecraft surface, while ions can only impact, for example, leading edge surfaces. This disparity can lead to a negative charge buildup, which can lead to ion sputtering, to arcing, to parasitic currents in solar arrays, for example, as well as reattraction of contamination, which is very important and crucial for as a problem in space. And so another key issue that is very important nowadays, especially when we are thinking about space sustainability, is the orbital debris impact. All areas of spacecraft have the potential to be struck by micrometeoroids traveling as fast as even 60 kilometers per second, which is really fast in space. Surfaces facing the ram direction are more likely than those in the wake direction to be hit with space debris. These can have a smaller velocity. They can be, for example, traveling with a 10 kilometer per second. Space debris varies with the solar cycle. This is probably one aspect that you have already covered in the previous section. And as the sun's activity increases, the atmosphere is heating up and increasing the drag on space debris in orbit. And large space debris are tracked so that the ISS can perform avoidance maneuvers, but there is no current way to avoid small debris impacts. Most of the impacts on return experiments have been small, and they're creating less than 0.5 millimeter diameter craters. So these are very important. And as you probably have read in different stories about the ISS, there have been small damages to the ISS because of this orbital debris. And it's one of the most important areas of research of the past, I would say, 5 to 10 years, to the point that the United Nations also is trying to mitigate this problem and prioritize it at the top of the agenda. And they're trying, especially the UN Outer Space Committee is trying to create possibilities of funding for further research. So if you have ideas of how to mitigate orbital debris, I would tell you to look for opportunities for funding, because there will be a lot in the next few years. So moving on here, this is also with extent to the previous topic, as we said. It's about where can we accommodate this type of experiments when we are testing different types of materials to see which one can sustain the space conditions more. Where can we accommodate them? So here you can see the Japanese experiment module exposed facility, which on the right side, and all these little places where I have numbered them from 1 to 12, you can see these are places where we can locate different types of experiments and expose them to space. This is called Kibo, by the way. It's the translation of the word hope in Japanese, and it's an external platform. It's used for research in the areas of communications, of space science, engineering, materials processing, obviously, Earth observation. And there are ways to monitor these experiments through cameras. This is how we see the degradation of the materials or not over time. And I have listed here the many different research models. It's 1, 2, 3, like 6 different modules that also accommodate material science research to assess different types of phenomena from, as I said, plasma, ultraviolet radiation, and more. So moving forward, I would like to have an overview of the key 20 breakthroughs in the past 20 years of science that happened on board the International Space Station. Some of you may have heard or read or even conducted research for some of these experiments. But I think it's good to have an overview of the different types of disciplines and how did they push the binaries of science forward. So the first one, as you can see, is fundamental disease research. There have been a lot of experiments on different diseases, on Alzheimer's disease, Parkinson's disease, cancer, asthma, heart disease. And if any of these conditions have impacted your life, space station research has also affected you, because a lot of the drugs and a lot of the therapeutic pathways were developed because of this research in space. So microgravity research has provided new insights. And without the interference of Earth's gravity, Alzheimer's, for example, researchers would not be able to have studied protein clusters that can cause also neurodegenerative diseases. And here you can see also a small result of the dopaminergic neurons that are depicted in microscopy in a culture dish. This is a very exciting result in order to study Alzheimer's. But also we had, cancer researchers that has studied the growth of endothelial cells on the space station. And endothelial cells can help supply blood in the body, and tumors that need to feed upon this blood to form and grow. So space station grown cells grow better than those on Earth and can help test new cancer treatments. And usually the platforms that they're tested on are tissue-specific or tissue-engineered small constructs. So Parkinson's disease as well and multiple sclerosis are neurodegenerative illnesses that damage the brain and the central nervous system, and they have been extensively studied in the ISS. And this is due to the fact that the researchers suspect that the damage that may be caused by Parkinson's disease may be the result of a glitch in the body's immune system. So NASA is interested in how spaceflight changes the immune system, since some astronauts experience strange effects following missions, including temporary activation of dormant viruses. So this is how you see now that human research is also combined with cell and biological research as well. So furthermore, here we have the discovery of steadily burning cool flames. This is a very exciting domain. When we think about, for example, fire, we typically think about heat, but special flames created aboard the space station keep things a bit cooler. So clearly, you probably have heard before that within the space station, everything is from materials that are not flammable. So when scientists burn fuel droplets in the flame extinguishing experiment box, something unexpected occurred. A fuel droplet appeared to extinguish, but actually continued to burn without a visible flame. So the fire went out twice, once with and once without a visible flame. So this is the first time ever that scientists observed large droplets of heptane fuel that had dual modes of combustion and extinction. So the second stage was sustained by what is known as cool flame chemical heat release. So this is a very exciting topic and has many different applications and translational value as well here on Earth. And here, the third one is the new water purification system. Clearly, this is an obvious application in many extreme environments and underdeveloped countries here on Earth. In space station's life support system, they developed the water purification system to provide the crew with clean air and also clean water in order to make it sustainable and make it a closed loop system. So the water recovery system purifies and filters the station's water, recovering and recycling 93% of the water astronauts in space. 93% is a lot, which makes them almost autonomous. This technology has license to adapt into an Earth-based water treatment system. And it's the first of many groundwater filtration system, which was installed also in places like, for example, Iraq. Station research studies like the aqua membrane have also tested out other innovative water systems, trying to translate these technologies to underdeveloped countries in need. Following another very interesting experiment is the drug development using protein crystals. So humans contain more than 100,000 types of proteins. Each protein has information related to our health. Studying these proteins by crystallizing them help us learn more about our disease and potential disease treatments. So protein crystal growth experiments conducted on board the space station provided insights into numerous diseases, from cancer all the way to gum disease. And one of the most promising results of these station experiments has come from the study of a process with a Duchenne muscular disease. This is a dystrophy, and it's an incurable, unfortunately, genetic disorder. A treatment for DMD based on this research in clinical trials, which is a major breakthrough in clinical research. Another investigation was the BCG5, which sought to grow the therapeutic antibody, which is Keytruda, in a more uniform crystallizing form. The goal was to improve drugs such that it can be delivered by injection as opposed to IV treatment. And this small differences in how we can provide a difference to a patient, it can be life-changing for patients in need. So this has been one of the most fundamental breakthroughs in science for the ISS. So following, we have the methods to combat muscle atrophy and loss. I assume many of you are very familiar with this type of research. Probably you already know that because of microgravity, mostly, but also because of radiation, our bodies, when entering space, are degrading in terms of their mass in muscle and in bone. And the effect of this microgravity degradation provides unique opportunities for research in order to reverse this phenomenon. So space studies have contributed greatly to our understanding of bone and muscle loss in astronauts and on Earth as well. Scientists have developed an exercise routine and also diet regimen that significantly reduces the bone and muscle loss that astronauts otherwise would experience during their stays station. These findings inform the physical activity and nutrition required on deep space missions, why probably you have seen, if you're following the astronaut missions, even on YouTube, you might have seen astronauts conducting countermeasure exercise to basically help their bodies fight the bone and muscle loss. Experiment that was mostly targeting on this area was the osteomics experiment, which investigated mechanisms behind inflammation and loss. Also, extensive rodent research was conducted, especially the RR team analyzed drugs and target myostatin, which influences the breakdown of muscles and bone. And researchers have even tested tiny chips for delivery drugs to combat loss. So as you can understand, this is a very key and important factor because to think and design future colonization, for example, in different planets or even the moon and Mars, it's very important that we tackle this problem. So the sixth is exploring the fifth state of matter. So 25 years ago, scientists on Earth first a fifth state of matter with properties totally unlike solids, liquids, gases, and plasma. The achievement garnered a Nobel Prize even for those scientists and changed the field of physics. So in 2018, NASA's Cold Atom Lab, which I assume many of you are familiar because it gained a lot of fame, became the first facility to produce that fifth state of matter. It's called the Bose-Einstein condensate. The Cold Atom Lab lowers atoms to ultra temperatures in order to study their properties in ways that are not possible on Earth. So this is why, as you can see, it is very possible to study fields that are very specialized, such as quantum physics on the ISS. And this study can provide insight to fundamental laws of quantum mechanics and could support of quantum technologies such as ultra-precise sensing and timekeeping. And here you can see in the picture NASA astronaut Christina Koch, who is a real astronaut. Actually, she was also in the NASA Academy that I have graduated as well from. And I'm very proud of her and I really admire her. And she, as you can see, she was one of the people unloaded and tested the Cold Atom Lab aboard the ISS in 2019. So this is a very famous study as well, one of my favorites. You can say this is about the understanding of how it's changed in microgravity. So before humans head to Mars or any other planet, we want to know what challenges we will face in terms of our pathophysiology. So long-term stays for the space station have allowed us to uncover and begin solving challenges that could be presented by the human response to space. For example, some space station astronauts unexpectedly developed changes, now known as the spaceflight-associated neuroocular syndrome. Findings include swelling at the optic disc and flattening at the back of the eyeball. After helping discover space station research has served as a platform to better understand this type of disease, the SANS disease. And we had the NASA's twin study where we have compared astronaut Scott Kelly this year in space with his Earth-bound twin brother, Mark Kelly. So one of them was in space and the other was as a control on Earth. And it provided insight the many ways long-term spaceflight affects the human body. Findings showed gene expression changed and his body reacted appropriately to vaccines while in space. So this is a very exciting research, and it was only possible because these two very bright brothers, they are both astronauts, which is also very rare. They're the only twin astronauts ever. So moving on, another very exciting experiment is the testing tissue chip space. Tissue chips are roughly thumb drive sized devices that contain human cells in a 3D matrix representing functions of an organ. This is very close to me because I have my PhD on regenerative medicine, so I'm very excited about this development. It's really cool that the ISS is funding this type of research. They represent a big step in the ability of scientists to test how those respond to stresses, to drugs, and to genetic changes. So the Tissue Chips in Space initiative seeks to use these devices in microgravity to better understand and improve human health, and it targets killer diseases in order to create comparable controls. So chips simulating, for example, lung and kidney and brain and intestine behavior all have been sent to the space station by a branch of the National Institutes of Health and the ISS US National Lab. So a lot of university labs are also collaborators for this experiment to be completed in the ISS. Following of another very exciting topic, which is stimulating the low Earth orbit economy. So satellite deployment, which a lot of countries from Asia and all around the world have invested money on satellite deployment and also conducting space research with satellite deployment. It's a vibrant commercial space economy. Through the ISS, many companies are able to access the space station and conduct research and technology development investigations in microgravity. And this is an area where you can potentially try to find opportunities to collaborate with private partners of ESA or NASA who are executing experiments to the ISS. Include well-known corporations, even for example, Procter & Gamble, which has used the station to study colloids with the goal of improving products such as, for example, the shampoo that we have at home and fabric softener. Smaller companies like Lambda Vision have leveraged the microgravity environment on the space station to improve the price used to create retinal implants, which is a very major type of research. Some research activities on station is becoming a significant business as well. Companies like Tax and TechShot operate commercial research facilities housed on the station, and they also have annual conferences on their research on the ISS, which I encourage you to go through. And there is a cadre of 40 companies that help researchers translate their experimental hardware and either small and light in order to be able to actually be hacked to the ISS. Commercial resupply as well contracts can bring science and supplies to the ISS, and they have helped as well to support the ecosystem. And there are many companies that do that, for example, Northrop Grumman, and even SpaceX that most of you know. Another interesting area of research where we have seen a lot of growth the past decade is the growing food in microgravity. So as humans expand farther from Earth, the ability to grow food, it is, the capability to grow, for example, vegetables and that have nutritional value is challenging for long-term missions where, you cannot have the same amount of cargo as you can have, for example, to the ISS. So fresh produce provides nutritious meals over multiple years and reduces cargo requirements. Many techniques for growing plants have been explored on station to prepare missions. And on August 2015, astronauts sampled the first space-grown salad. So they actually ate the salad that they grew. 8 types of leafy greens have been in a veggie facility for astronauts to eat, and they are fine-tuning the best techniques to actually farm them. So So during a mission, for example, to Mars, where we will need a lot of nutritious foods and vitamins, and it's not going to be easy to transport because of the degradation that may occur due to radiation, it'd be very important to have fresh crops and have these technologies to provide it so that they can actually grow food on space in a colony. Moving forward, there is the CubeSats from station. This is a major research. CubeSats are one of the smallest types of satellites. You can see it in the picture as well. An inexpensive way to perform science and technology demonstrations in space. Once compact cubes can reach Earth orbit is hitching a ride to the space station, where they are deployed from an air, sharing the cost of the rocket launch with the other groups launching payloads to the space the space station. They can make deploying a CubeSat more affordable, so that it's a cheaper way to conduct research and transfer your experiment to the ISS. Some of the first CubeSats released from the station were by the Russian cosmonauts while they performed the spacewalk. In 2012, crew members began using the Japanese Kibo module airlock to deploy CubeSats. Soon after, American company Nanorox, which is a major player in the field, started operating a Morobloyer. And one of the first customers, another company, Planet, also deployed CubeSats to take high-resolution photos of the entire Earth each day for Earth vision studies. Planet deployed, Planet the company, deployed several generative CubeSats, demonstrating the viability of their technology and their business model. And so we have NASA's, of course, CubeSat launch initiative that provides a pathway to conduct research in space. And they are also linking educational institutions, they're linking nonprofit organizations and NASA centers and programs. So this is quite an approachable type of venue to conduct research into the ISS. Following the planet monitoring, this is, of course, one of the major and the most key type of research that NASA is doing. Here you can see I'm with astronaut Tim Peake, who is a British astronaut who is working for ESA, the European Space Agency. All the astronauts are basically training for planet monitoring, regardless of their background. For those who don't know, when somebody is selected as an astronaut, as a candidate, he starts with training. It lasts for 2 to 3 years, where they learn different disciplines of science that is complementary to their existing knowledge. For example, those who are engineers, different types of science from biological domain, the physical domain, the geological domain, and those who are, for example, who don't have experience in let's say they take instruction lessons, but also all the astronauts, before they even into a mission to have particular experiments that they need to conduct in space, they take training on basic scientific domains that they absolutely need to know, as is planet monitoring, and also learn how to use different type of scientific cameras to take photos for different experiments that are, for example, observing the types of meteorological phenomena that are happening on Earth, or even the climate change. So the view of Earth from the space station, as you can see in the picture, it's a life-changing view. Very few people can actually see and photograph in person. But this does more than creates just beautiful image to share in NASA social media. This taken by the astronauts can help track the evolution of our planet alongside the suites of tools inside and outside the space station. And the ISS, as I said, is a robust platform for study Earth's water, air, land masses, the vegetation, and analyzing how water stresses plants. And there are many experiments that have conducted. The eco-stress experiments are a very known one. The JET experiments are very known in the same areas, analyzing carbon stored in the forest. And though the many experiments collect data individually, together they provide a set of measurements that pushes the leading edge of environmental research. And nowadays, I add that there's another domain of knowledge that is added of this environmental research, because artificial intelligence, creating machine learning, is to screen through all these different data sets that we have from 20 years. And they're providing new insights that we have not before. And this is another very interesting piece of research that is also being used to prevent catastrophe and prevent disastrous events and fires. And this is really an interesting time to get involved into the Earth studies. Following, I don't know if it moves. Okay, now we have the collecting data on more than 100 billion cosmic particles. This is a very interesting piece of research as well. Many scientists theorize that stars, planets, the molecules that comprise them are less than 5% of the mass energy content of the universe. The rest is dark matter, invisible matter that cannot be detected directly but can be inferred. So we're using spectrophotometers to actually look at the evidence of this substance space station. And this has been done for the past more than 10 years, I think from 2010 or 11. And more than 100 billion cosmic particles have been observed. So major instruments that we use, the alpha magnetic spectrophotometer 02, provided research around the globe with data that can help determine what the universe is made of and how it began. So it's a little bit of the Big Bang theory and how everything started. It also has collected data on cosmics, which is very important, and how these rays travel through space and what produces them. I think you have a few questions. I don't know what kind of equipment is available. Oh, yes. Thank you, Saina, for your question. I will give you a little bit of an overview of the different equipment, types of equipment that exist on the ISS in the later stage of the presentation in a few minutes. So be a little bit patient. And here you can see another very important is on understanding pulsars and black holes. I assume some of you are into astronomy and different type of research that are tackling these issues. Two tools installed on the outside space station have worked in tandem to advance our knowledge of pulsars and black holes. One of NASA's Neutron Star Interior Composition Explorer, it has the nickname of NICER, and all sky X-ray image, it's called MAXI. This is from the Japan Aerospace Exploration from JAXA. So in 2018, MAXI detected a new X-ray source and it provides a new knowledge. And shortly after, NICER began monitoring and determined it to be a black hole, which was a binary system containing a black hole with a mass several times the sun, which was a major breakthrough in the field of black holes. So with this new X-ray source became one of the brightest X-ray resources in the sky. And NICER traction of the system, its measurements help us understand how the inner edge of a black hole's accretion disk, which is called the corona, changes in size and in shape as a black hole consumes material from a star. So this is what you can see here. This is an illustration. It's a simulated event that was depicted through spectrophotometer. Following, of course, a very major and very relevant piece of research is the student-driven research that can access many different studies that are conducted in the ISS. Of course, I was one as well of those that have had the honor to work on different types of experiments to the ISS. And when I was in NASA Academy and later on at NASA Ames and later on NASA FDL, it is a very interesting and very important piece of research because, you know, there are programs that have given access to elementary and also college and graduate and postgraduate students to space, and the chance to take advantage of the microgravity environment aboard the space station. There have been more than 1 million students that have participated in EarthCam program, for example. Unfortunately, most of them are American citizens, but there are a few programs that are open to different students depending upon the era. Unfortunately, because of COVID now, from what I know, there are not a lot of that are accepting foreign national students, but I assume that in the next year, it will reopen again, the program. Of course, there have been many other programs that have been opened up to students. The Genes Inspiration, for example, the Guardians of the Galaxy Space Station Challenge, and you know, a lot of challenges like that you're taking now with the Singapore Space and Technology company. There are a lot of challenges as well with ESA and NASA, and their competitions have given access to design experiments that have actually flown orbit. And millions also of children have participated in Tomatosphere, which is with tomato seeds exposed to space or space simulated environments, and seeds that have not, allowing class to compare how seeds grow, which was a very fun and interesting experiment. And also there have been opportunities to interact and connect with astronauts themselves and learn more about their daily lives and how they even went from the, from all this career pathway of being selected to be an astronaut and being trained and go and flying to space. So I'm sure that there will be a lot of opportunities to come, hopefully in COVID-free times. The following one capability is the capability to identify unknown microbes in space. This is a very important project. Being able to identify microbes in space in real time without having to send them back to Earth for identification is revolutionary for the world of microbiology and for space exploration as a whole, I would say. The Genes in Space team proved this can be done when they completed the first ever sample to sequence process entirely aboard the space station in 2017, which we thought wouldn't be possible before. So crew members collected the sample, isolated the DNA, corrected, and then sequenced it, the unknown DNA. In the months leading up to the test, an astronaut, which you can see is Kate Rubins, one of the most extraordinarily brilliant women that have been selected to be an astronaut. I admire her greatly. And she also conducted the first DNA sequencing, which for those of you who know how to do a DNA sequencing in a university lab, you would appreciate the difficulties that she had to encounter to make it happen in the restrictive environment of the ISS. Following, we have the opening up of the field for colloid research. This is a very major branch of research. We have a lot of materials that we use here on Earth, from toothpaste, 3D printing, pharmaceuticals, and detecting shifting sands even on Mars and even other planets may not seem related to other at all, but all these they come down to have to colloid research and improvements thanks to many years of research that happened to the ISS. So pictures of tiny particles suspended in a liquid colloids occur in many forms. These include natural mixtures such as milk and muddy water, as well as a range of manufactured products, from shampoo to medicine to salad dressing. So space station research has explored subjects such as stabilizing these mixtures and colloid behaviors that can be applied to products on Earth. Following, we have the evolution of fluid physics research. So fluids, this is a major domain. Fluid covers all our planets. You know, water is one of the sources of life, but sending fluids to space can help us better understand how their properties evolve over time. So space station fluid research began with a fundamental analysis of how fluids behave in microgravity. That research has evolved into the testing of advanced medical and heat transfer systems. So also rodent research tested tiny nanofluidic devices, for those of you that are in the field of nanotechnology and microfluidics, and they implanted them under the skin in order to allow for continuous delivery into a patient system. This is a major breakthrough in the microfluidics and nanofluidics technology. This process can reduce the need for frequent injections or pills because you have an implanted nanofluidic constantly underneath your skin. And a series of experiments used microgravity to study also capillary forces, small that move a fluid along a narrow tube. And systems using capillary forces can be simpler because they rely on shapes and fluid dynamics rather than machinery in order to move the liquid. Another type of research that many of you, I assume, have definitely heard of is 3D in microgravity. And I had, for me, it was extremely excited because it's part of my education as well, particularly 3D bioprinting. But having a 3D printer on board the ISS for me was fantastic news. Also, I had the honor to be with in the training of astronaut Barry when he learned how to operate the 3D printer. And as you can see, we all had a lunch and dinner afterwards to celebrate his successful completion of his training, because as you probably have realized, all the astronauts are tested every time they are learning how to operate an experiment. And so they actually have to go through exams to showcase that they can perform the experiment ISS successfully. So the first 3D printer flew to the space station in 2014. It was developed by Made in Space. The printer produced dozens of parts that researchers analyzed and compared with those made on the ground. This was in order to compare differences of how a 3D printer is operating in microgravity versus in atmospheric conditions we experience here on Earth. Analysis revealed that microgravity had no significant effects on the process, with great result for NASA and ESA, and demonstrated that a 3D printer can be used, for example, tools and different types of structures. Later experiments tested using resin plastic to print objects and using a specialized bioprinter to print human tissue, which was a major breakthrough in science. So the biofabrication facility took small steps towards printing human organs, actually printing human tissue blocks in microgravity using ultrafine layers of bio ink. And finally, here we have the final issue responding to natural disasters, which is of course extremely important for defense strategy here on Earth and for the protection of the human population. With GRU handling camera imagery as a core component. As I said, this is a very major part of their training of all the astronauts. The station has become an active participant in orbital data collection, support disaster response activities around the world. So astronauts learn how to observe different types of phenomena and then snap images of disasters, such as, for example, storms or fires. And throughout their progression, they're documenting cloud covers or flooding of water and the changes to the land. And these pictures are then sent back they're mounted to the space station cameras. They are sent back to Earth, and they can be used to check power has been restored to cities after a disaster, for example. And nowadays, we also have artificial intelligence algorithms backing up the analysis of these images, and they're creating real-time diagnostics in order to provide information as to, for example, which areas are at risk, if some areas need to be evacuated early. So this is a very exciting time for this domain. So I will go on now to give you a bit of an overview, a very summarized overview of the different purpose facilities that exist on the ISS. You have to go through, and if you find something that you think could be applicable to your own proposal and your own research, you have to go through the technical parameters and understand more how it works and what type of experiment accommodate. But we will go through a little bit and have an overview today. So there is the multi-use lab facilities, as you see on the right. They expedite processing of experiments on the space station. There we have the microscience glove box that you can see underneath. This is a very key feature of the ISS. We have two glasses, and mostly this is used for microbiology research, but also for other devices that need an isolated environment that is sterile. And then we have capability enhancements, which means that every company, especially when we have public-private part for a particular experiment, meaning that private companies are co-sponsoring a particular event, we have additions to some of the infrastructure that exists in the ISS. And for this reason, if you think that you require a particular technical facility or something that, or an instrument that you think that is not one of the core ISS equipment, there is a chance that this might be on board. The different companies have also flown extra components and equipments to facilitate different types of research. So we have external accommodations. These are outside of the ISS. They are attached payload platforms. They allow from in any direction desired, Earth, Sun, space. These are more for observational experiments, deep space, and on Earth. As we have already explained, that there is, the Japanese airlock for small satellite orbital deployers, the KIBO component. And also we have the alpha magnetic spectrophotometer, which can scan through space. And there are as well several expansions on the remaining ports for the payloads and many different technicalities that to this extent you might not need to go through every single port and different, for example, attachment that a different module may have. You might want to have the very basic overview of it. Then we have the utilization enhancements. These are different enhancements for, especially for experiments that have to do with storage facilities, especially on water, and how it is handled, how it is filtered. There are orbit stowaways and spares, for example, that are improved on orbit inventory. There are social management systems, and there are data communication systems. This may be important to you if you want to deploy a machine learning algorithm, because you have to go through computing power that exists on the ISS, and also understand that there are some local difficulties in the way that, for example, we can train a ML algorithm on the sense that your uplink might be very reduced, and the size of the data of the model itself have to be restricted and downsized significantly. So there are several facilities like telemetry and video, and several communication apps as well, which are, of course, basic facilities. Then we have physical sciences. We have the combustion system. This is a rack that allows for research the effects of gravity. There is a lot of research that are happening, as I said, in fluid physics and material sciences, and we have the equivalent racks that are allocated just for these experiments. So for fluid physics, you have the fluids racks, and the material science, you have the research rack, where, for example, you can research the melting and solidification of metal alloys, different capabilities of different types of materials, as we discussed. Then we have biological research capabilities. As I said, there are many different bioreactors that are flown to Earth, but you have to check in every mission. So the ISS has different missions. You can see them in the official page, and see in that mission what type technical equipment they currently have, because some of the bioreactors are flown back with the experiment to Earth for analysis. So you have to be careful with this. As you can see here, there are the plant seeding growth research, for example, the fruit fly research, which is a very big component of behavioral monitoring, for example, with fruit flies. Then we have different type of automated labs. Some of them are bioreactors, some of them are smaller multi-purpose platforms, as you see on the one on the left on the slide. They have certification systems and basic chambers to grow and incubate types of organisms. But again, you have to check what sort of capabilities you need, how many well plates you need, what sort of media you need to use, what buffers you need to use, what gaseous exchanges you need to have. So all these play a factor into what type of equipment you need to use at the end. For biological research, as I said, for rodent research, there are a lot of more capabilities. There are habitat transporters. There are also scanners for bone density. And also, of course, cold storage. This is for freezing and biorepositorying the different cells, tissues, and different animals that might be needed to be returned back. So there are many different systems that you can use. Then there are, of course, wet analysis as well, water monitoring suit system, the nanoracks, as we mentioned before, microscope, different microscope units that you can use to monitor the progression of the experiments. But usually most of the experiments, especially in biological research, have a limited timeline of growth. It is quite tricky in the ISS to perform like a 6-month experiment, for example, on stem cells, let's say, that need to be passaged, that need to be regrown on different type of plastics and vehicles. So in terms of now Earth and space science research capabilities, as you can see, there are many different platforms that are, as I said, they're changing over time. They're having some enhancements. Here are some views for the Window Observation Research Facility and all facilities that are overseeing different phenomena on Earth. And as you can see here, the ISS provides coverage of 75% of the Earth's surface and 90% of the world's populated landmass every 1 to 3 days, which means that it's monitoring almost all the surface of the Earth. There are also external science platforms. As I said, these are not always the same. They're not always the same on board the ISS. So you have to check on the particular timeline of your experiment, which ones are available. And closing this presentation, I would like to give you a small overview of some experiments that you might not be very aware, but they are in many different domains. For example, I have worked on the grip assessment experiment, which is an experiment that is conducted in order to assess how astronauts are holding onto different materials. This is extremely important for EVAs, for extravehicular activities outside of the space station, and also to design better system for maneuvering and better also gloves for the astronauts. So in the weightless environment of the space station, astronauts are like infants. They're learning to adjust because it's a completely different environment. They're learning to adjust to microgravity in which they find themselves. The objects have no or very minimal weight, which is an important indicator for how are perceiving this changing and how much grip force you need to apply on an object when moving it up and down. So the inner ear as well no longer tells us which way to go up, and which also it doesn't, you are losing orientation, and this is diminishing your capability to perform and grip things in the optimal way. So naturally our brains are a little thrown off and our coordination is disturbed, and this is why researchers, experiment was from the Institute of Neuroscience in Brussels. They studied how long it takes for our brains to adjust to this dynamic, and this is astronaut Alex Guest who performed the experiment, and Alex performs a series of different movements while gripping a purpose builder that measures grip forces, the moisture as well, and the acceleration, and how his body also adapts to situations in which there is no up and down. Another experiments that I have worked on, again with Alex Guest, was the space tech thermal regulation experiment. Which again, the key issue that we had to deal with was the lack of convection in space that affects the way heat and sweat are transported and absorbed into an astronaut's clothing. This is particularly important in cases where the astronaut is doing an EVA and he cannot change, for example, his astronaut suit. Astronauts often report sweating more during exercises in orbit compared to exercises on Earth. Heat envelops their bodies like an aura. And as you can see in the simulation on the left side, and high performance fibers were assessed on the space station. How comfortable these garments were in comparison to conventional cotton garments in order to redesign the suits. So the textiles would have to be specially adaptable for use in space. And this is why we investigate new fabrics with better thermal and sweat management to the astronaut's cooling mechanism and to reduce microbiological contamination on the spacecraft. And finally, before I leave you, another experiment that I have worked for at NASA was the creation of a machine learning algorithm to support the AI doctor to enable wearable diagnostics, autonomous healthcare diagnostics in space, and also to the ISS. So we have developed, as you can see on the left, an AI architecture where we were integrating wearable and symptomatic and clinical symptomatic data with the goal, the aim, to create a diagnostic tool for a condition, a cardiovascular condition. It's called atrial fibrillation. And in order to do that, we also had to create the synthetic medical data. But as you probably realize, when we're trying to create AI diagnostic algorithms, we have to have an input of the different types of diseases, as when it comes to, for example, ECG signals from space with the microgravity component. And this is something that does not exist. So how can you make, how you can create an AI diagnostic tool without having synthetic data automatic from space? And we were one of the first teams to ever make synthetic medical data that are supporting and informing the AI doctor to provide capillary research. And as you can see here, this is astronaut, the Canadian astronaut who was wearing the wearable. This has sensors underneath, and the AI algorithm was running on board as well to provide him the diagnostics and real-time monitoring. So thank you for your attention, and a few pictures of the different types of projects that I was allowed to experiment a little bit. You know, the glove box, as you can see on the left, rovers, as well as, you know, the Martian surface and the different geological components that we were finding. And on the right side, this is the replica of the ISS as it is in the European Space Agency, where I had the honor to work on the astronaut training. And I'm happy to provide any other information and feedback today.
Yeah. Thank you, Eleni. We might have some feedback. Okay, so we are going to jump into Q&A. So I'm going to lump some of the questions together, just so to kind of save time. But so we have a question from No, I think is that, I'm sorry if I mispronounce your name. He says that if radiation is not such a big issue for astronauts on the ISS because the magnetic field of the Earth prevents most of the radiation from reaching Earth, then how exactly do astronauts collect radiation samples? Someone also asked, how do you collect samples such as UV rays, plasma, or other similar particles?
Right. There are spectrophotometers that are located on different instruments that are in deep space and not just on the ISS. And these are giving us measurements for type of radiation and what radiation waves we would perceive for if we were to leave Earth and arrive to Mars and float Mars. So this is the reason why we have these measurements. Definitely, as you said, this is a very tricky type of research because we don't have physical experiments where we can, for example, have in vivo animal research in deep space and return these type of samples back. As you can, first of all, right now, this is not a biologically ethical project, and secondly, the logistics would be impossible to implement. This is why you're right, we have that. The second thing we do have is that we have some facilities that are approximating some radiation levels at NASA. So we are having simulated radiation experiments, and there you can, for example, irradiate samples with types of frequencies, and this is the way that the biological research is on this topic. But definitely, it's a very difficult topic to investigate.
So yeah, Noah asked also, why was NICER, or the Neuron Star, if I'm not wrong, the Neuron Star Interior something mission attached to the orbiting platform of the ISS and not any other satellite? What feature of the ISS makes it an optimal choice for this?
Well, it's not the only. First of all, the computing power that you can have in the ISS is higher, right, than in the other satellites, the only navigation satellites or telecommunication satellites. So the ISS is an actual lab that has many different modes on and can provide analysis on board, which is something that most other satellites cannot provide. So on the other satellites, you have to have a download link and send data back to Earth for analysis. So definitely, I assume that it would be a capability that some other satellites could carry, but yes, it's just superior, and this is why it was chosen.
I think a lot of times experiments are done on the ISS because also it's in constant communication. You can basically get almost well, not instantaneous, almost without communication with the astronauts.
Absolutely, that's one of the major features as well. That you have humans on board as well. It's not just the interface that the computers are managing. So definitely, that was one of the reasons. And of course, there are some political issues in the sense that the ISS can host different experiments, and there's a policy agenda in the ways experiments can be hosted. So different companies can collaborate, and there is a regulatory framework. While if they didn't use the ISS, then they had to seek the facilities and the capabilities of their own country. And different countries have smaller or larger capabilities in satellites. Some countries have very few, one only, and some other countries have more. The ISS is a neutral environment where you can have scientists, you can have many different resources, and a lot of different type of support to implement a project there. This is why I think it makes sense for most companies to seek a collaboration with the ISS. Yes, I think that TT, but you are saying that, do you think radiation shielding materials can be studied? Absolutely, they can be studied on the ISS. Actually, they're one of the major topics of research as well. There, as you said, radiation exposure is not as high as, for example, on the surface of Mars. But yes, there are several studies already in the past few years on different types of shielding for radiation, but if it is still in its infancy, it's not considered to be to have a major breakthrough topic, apart from having lead as a formulation to protect from radiation. Still there's a lot of growth in this area.
And actually, I think this might be a good experiment to be doing on the external platforms.
Absolutely, yes. Adjacent to some modules, yes.
Yeah. So the external platform could be very good for what you're thinking of doing. Just because there is obviously once it's held outside for a period of time. I believe. Can the ISS be too full for experiments?
Okay, there have been more than 3,000 experiments that have been conducted to the ISS today. It is true what you're writing, in the sense that there are a lot of experiments that are prioritized and they are scheduled for different time slots in the ISS. And if for any reason you lose your time slot, you might need to wait for years before you are back into the sequence of, for example, your your experiment to the ISS. And I can tell you, for example, in 2014 or 13, I don't remember, a cargo exploded, unfortunately, a rocket that didn't have any astronauts. It was just a cargo of a rocket sending different types of experiments to the ISS. And because all the experiments, of course, they exploded, they couldn't again put back different type of the same type of experimentation back to the ISS because there were so many scheduled experiments on board. So yes, it's an exciting platform, but I hope that your generation will see another ISS. The ISS version 2.0 or 3.0 will be better, and one of the plans that is talked these days is to perhaps create a similar ISS structure, a lab that is orbiting in a distance between the Earth and the Moon. So it's going to be further away. And this also will give us ability to research the radiation exposure in a better setting than it is on the ISS. So I hope that you will see this very soon. And it looks like there are already talks about the funding and the different that want to support it. So I hope that it will be implemented along with, you know, Moon Village project, which is now on the works as well. Hope this will be
true. It's true. The Moon Village project has been quite active recently, or a lot of focus around it. So maybe in the future, you guys might have a research platform on the moon itself. So yeah.
Yes, I think it's not. There is a good chance if you know all the talks and the policy consensus is there. There is a chance that it might be implemented in the next 20 years. So I don't think it's that far away. It probably is close. But thank you all for all your questions.
Someone asked, how exactly would we be able to make use of the equipment of ISS?
How we can make use? So, okay, there are different paths. So you can either try to send a proposal to a commercial company like NanoRacks or other private sector company that is already having a contract with the ISS, and they're already deploying different types of experiments in many different fields to the ISS. The easiest pathway is to win a space challenge competition. And especially, and I'm not saying this just because of our webinar, if, for example, you are the winner of the SSTL and you want to reach out, for example, to ESA and NASA entities, your chances are higher to get this and see whether, you know, your experiment can actually support goals of the two different agencies as well. There are a lot of student projects belong to the ISS because they have won space challenge competitions, more than 20. And then the second basic way to send experiments is if you are, for example, a student, especially in a university that is located within the territory of a big space agency within the US or Japan, you know, China, it is possible to send a proposal to a solicitation of the space agency. A solicitation is like an open competition. They have constantly around all types of fields and around many different topics that have open solicitations. You can ask your supervisor and a team of officers to help you co-author a proposal. Usually it's around 20 to 30 pages. It's similar to what you will prepare for the Space Challenge competition. This is why I'm saying that, you know, the groundwork you do today might be actually super useful in 2 years or 3 years from now, even if you don't win this competition. And then this proposal is sent to for evaluation and review back to the agency, and they actually do pick many of these projects. And similarly to what I have explained to you in the slide about the different roadmap that you have in this research, it actually, after 2 or 3 years, it's actually flown to space, and it's a very exciting experiment to go through.
Yeah, and then maybe to clarify, is that yes, everything that has been shared today, it's open for you guys to potentially use in your project. Yeah.
This was an overview of information that are readily available in the internet. You can find information at NASA's website and ESA's webpage. So you can find more information about the different technical parameters. But I would say try to not have specialized information, try to have a basic concept and an idea, and then try to support it within a structure that already the ISS, and try to frame it in a similar manner to an experiment that has already in space. And then I think Jillian has already given you some instructions of what she to abide with. I think that you have a mass threshold and you have different thresholds for the experiment. So you have already some guidelines to follow.
So all these are just guidelines for you to follow. Obviously, if you have an idea for an experiment where you don't think any of the equipment on board is suitable, you can feel free to suggest equipment that you might need. But obviously that's a bit harder to find space on the ISS because there's new equipment and things like that.
Unless you need something that you can 3D print, and then you can propose that there are parts that can be 3D printed on board. So then you can actually do it.
Yeah. So those are some of the things that you can think about. But yeah, I think we've gone a bit over time today, so I'm sorry for taking out too much of your time on a Saturday. I hope everyone has a good weekend. But thank you all for joining us today, and thank you, Eleni, for that insightful sharing. I hope everyone please give Eleni a big thank you for everything she shared today. We will share the recording with all of you as per usual. So yeah, you can look out for that in your emails in the coming week. Otherwise, that is all we have for today. And I wish everyone a good weekend.
Bye, everyone. Thank you so much.
Thank you, Eleni. Thank you, everyone.